Today, our topic is Introduction to Filters. So, before going to filters, I would like to explain about rectifiers. So, previous class we talked about rectifiers. So, what do you mean by rectifier? Rectifier is a converter which converts AC signal into DC signal. That is, so this one is AC signal. AC signal means alternating current to DC current. DC current means direct current. So this is the purpose of rectifier. So rectifiers are two types. One is half wave rectifier and other one is full wave rectifier. We will see outputs. So half wave rectifier. So this one is half wave rectifier. So input is AC signal. AC signal means alternating current. What is the output of half wave rectifier? We will get only one half cycle is rectified. So this is the half wave cycle, half wave rectifier output. So half wave rectifier output is a DC, but it is not pure DC. Actually, DC signal is like this. Instead of this one, we will get pulsating DC. So we go for full wave rectifier. Full wave rectifier. So full wave rectifier input is AC signal. AC signal. Full wave rectifiers are two types. One is center tapped full wave rectifier and other one is bridge rectifier. So both cases we will get full rectified output like this. See this one, and this one. This is the full wave rectifier output. Okay. So, but full in half wave rectifier only 40.6%. So AC signal is converted into DC signal only 40.6, whereas in full wave rectifier 80.1% will convert from AC signal into DC signal, but it is not pure DC. It is a pulsating DC. Right. So these full wave rectifier output, that is DC signal, pulsating DC signal, is given to the filter, F is given to the filter. So full wave signal. So this is the full wave rectifier output is given to the filter. So what is the output? Output is, it is a DC. It is not pure DC, it is a pulsating DC. Okay. So this is the rectifiers. Half wave rectifier output is this one. Full wave rectifier output is this one, but efficiency is more. And full wave rectifier output is given to the filter. Okay. This is the way. So this is the full wave rectifier output. Full wave rectifier output is given to the filter, So we will get DC signal. This is also a DC signal, but it is not pure DC signal. It is a pulsating DC. So pulsating DC means some AC components are mixed in DC. So these AC components, we also call it as a ripples. We want to eliminate these ripples by using filter. Okay. So full wave rectifier output is a DC signal, pulsating DC signal is given to the filter. So filter output is like this. See, instead of getting this DC signal as a straight line like horizontal, we are getting some AC component pulses. So these, see, this peak to this peak, we call it as AC components. So AC components are unwanted things in output side. AC components are unwanted things in filter output. We want to minimize these AC components, that is the ripples, by using proper filter design. So proper filter design, we will get exact output. So for example, we have to design some good filter. So filters are different type. I will discuss within a short period. So filter output, it is a proper filter means filter output is exact DC. So such a way that we have to design a filter. So at the output, there is no AC components, only we will get DC components, such a way that we have to design a filter. Okay. So full wave rectifier output is a pulsating DC is given to the filter. Okay, filter output is DC signal. It is not pure DC. It is also a pulsating DC. So filters are four types. One is L filter. L filter. Second one is C filter. L filter. Second one is C filter. First one is L. Second one is C filter. Third one is LC filter. Fourth one is CLC filter. LC filter or CLC filter. Okay. So LC filter means inductor filter. L for inductor. Inductor filter. C for capacitor filter. LC for inductor capacitor filter. CLC for capacitor inductor capacitor filter. So inductor filter means we have to add one inductance at the output like this. So this is the RL. So this is the L. So in series, we are connecting one inductance. We call it as inductor filter. Across the load, we are connecting one capacitor. So this is across the load RL. This is the RL. So this one is C filter. This one is L filter. This one is C filter. So LC filter is nothing but combination of C and L. So this is L filter. This one is C and this one is resistor. So we call it as this one is CL. So LC filter. So LC filter is also called as L filter. We call it as L-shaped filter. So it is L-shaped. This one is L-shaped. Next, CLC filter is nothing but like this. I will explain in detail about these filters. C, C1, C2 and L. So this is the CLC filter. It is also called as pi filter. It is pi shape. This is the pi shape, pi filter. Okay. Pi filter. Okay. So filters are four types. One is L filter, C filter, LC filter, CLC filter. Okay. So we know that capacitor blocks DC. So this one is capacitor blocks DC and it allows AC. So for example, it is a sinusoidal signal, full wave rectifier output. It is AC component, DC components. Only we will get DC only. Only we will get DC only. So we know that capacitor blocks DC and it allows AC. So capacitor allows AC and it blocks DC. So we know that what is AC signal? It is an alternating signal. Frequency is not equal to 0. Whereas in DC signal, frequency is equal to 0. So what is the reactance of capacitance? So reactance of capacitance Xc is equal to 1 by omega C. So what is omega C? So omega C is nothing but 2 pi f. Omega is nothing but 2 pi f into C. Since omega is equal to 2 pi f. Omega is equal to 2 pi f. Okay. So omega is equal to 2 pi f into C. So it is the reactance of capacitance. X is the reactance of capacitance. We know that what is the reactance of capacitance whenever DC signal. So frequency is equal to 0 for DC signal. So 1 by 2 pi into F. F is equal to 0 for DC signal into C. So 1 by 0 is equal to, it is infinity. Infinity is nothing but open circuit. Open circuit. OC. Open circuit. So open circuit, what is the open circuit symbol? Open circuit symbol is like this. Open. It is open. So there is a no connection. If frequency is equal to 0 means it capacitor is open. So for DC signal, capacitor is open. So there is no signal. It allows only AC signal. So AC signals are coming this way and coming this way and reaches to ground. So every circuit there is a ground. So that AC signal is grounded. Only it allows DC signal. Finally, we will get at the output side DC signal. Finally, we will get the output is DC signal. Okay. So one of the student wrote, it is a remember, it is like a joke. Why does a capacitor blocks DC, means a direct current, but let's AC passes through it. One of the student wrote in exam, see, it is not, it is a joke. Take it as a joke. So it is really simple. Student wrote like this. If I give a nice look at a symbol of capacitor, so capacitor symbol is like this. Now when DC comes, DC, we know that DC is the direct current. It is a horizontal line this way, like this. When DC comes, so this dot line. So this DC comes, so capacitor blocks. So there is a line, vertical line. So that DC signal capacitor blocks. So it gets blocked. But whereas in AC signal, see, AC signal is like this now, AC signal. So AC signal is like this. See, AC signal, capacitor, it allows AC signal. See, there is a gap. There is a gap in between vertical lines. So AC signal is moving this way. That means capacitor allows AC signal and it blocks DC signal. Remember in this way. Okay. Now first we see the capacitor filter. Okay. So we know that. So this block we call it as capacitor filter. Just now I explained. So capacitor is connected across the load resistor. We call it as capacitor filter. Inductor is connected in series with the load. We call it as inductor filter. So this block we call it as capacitor filter. This is a filter. Other half, this one, other half we call it as, what is this? full wave rectifier, center tapped full wave rectifier. So center tapped full wave rectifier output is, so first block output is like this. So first block output is like this. Okay. So this DC signal, it is a pulsating DC signal, is given to the filter. So filter output is, we will get like this. Filter output is like this. Instead of getting a horizontal line, we will get this pulsating DC. Okay. Even though we are using filter, some AC components are mixed. So by using proper C and L and RL components, we will remove these ripples. Okay. Understood this one? This one is this one is full wave rectifier output is given to the filter, capacitor filter we will get. So I will explain in detail by using this graph. So we know that this is the dotted lines. See, you can observe my mouse point. This is the full wave rectifier output. Full wave rectifier output. So this dotted line, we call it as full wave rectifier output. Okay. So this is the full wave rectifier output, dotted line. So you can observe this. So this one is maximum voltage. See, this is the peak. Maximum voltage means VM. Okay, understood? So we are connecting capacitor. So when positive voltage is given, means positive off cycle is given, this capacitor is charges fully to the secondary voltage. For example, it is a 50 volts, means transformer secondary is 50 volts, means this one is 25 and this one is 25, because it is a center tapped. It is divided into two. Okay, secondary voltage. So this secondary voltage is for charging the capacitor. Secondary voltage is for charging the capacitor. See, capacitor is charging. Capacitor is charging. Okay. So during the positive off cycle, so the capacitor up to peak value. So the capacitor up to peak value of the transformer secondary voltage VM. This is the VM, and we'll try to maintain this value as the full wave input drops to 0. So it is the transformer secondary voltage is VM, full wave is down to 0, up to it maintains the peak value, slightly discharging here. So the capacitor will discharge through RL. So here capacitor is first, it is charging up to maximum point. Up to maximum point means this one. So capacitor, this is the capacitor charging up to maximum point. Then it discharges to RL. So discharges to RL means, so from maximum point to this point, capacitor is discharged through RL slowly until transformer secondary voltage again maximum. Until transformer secondary voltage again increases to its greater than capacitor voltage. Understood? So the diode conducts for a period which depends on the capacitor voltage. It depends on the capacitor voltage. Okay. The diode will conduct when the transformer secondary voltage becomes more than the diode voltage. The diode will conduct when transformer secondary voltage is more than the diode voltage, then diode will conduct. That point we call it as cut-in voltage. That point we call it as cut-in voltage. Okay. That point we call it as cut-in voltage. Next, what do you mean by cutout voltage here? So this is the cut-in voltage. Cut-in voltage. This is the cutout voltage. Cutout means, what do you mean by cutout voltage? The diode stops conducting when the transformer voltage becomes less than the diode voltage. When transformer voltage becomes less than the diode voltage, then it is called as cut-in voltage. Okay. So this is the charging, this is discharging. So this point from T2, so from this is the discharging up to here. So T2 is the discharging point. This one is the charging point. T1 is the charging point. Okay. So the cut-in voltage to peak point, we call it as RMS voltage peak to peak. RMS voltage peak to peak. Okay. See, the charge, generally capacitor charging is equal to capacitor discharging. So this is the phenomena. So the charge it has acquired. So charge acquired means VRPP, means RMS voltage into C. This is the charging period. C. This is the charging period. Okay. This is the charging period into C. So the charge it has lost IDC into T2. IDC into, this is the discharging time. So this is the discharging time capacitor through R, discharge through RL. So this is IDC into T2. IDC into T2. Okay. So we know that charging is equal to capacitor discharging. Charging is equal to discharging. Okay. So this is the, we equal this point 1 and 2. We will get this third equation. Okay. So VR RMS is equal to, so this is a, we consider this equation is a triangular. This DC voltage look like triangular. The triangular equation, we can write a VRMS of triangular is, this is the standard equation, VRPP by peak to peak by 2 root 3. When it is a triangular wave, RMS value of triangular wave is this one. Okay. RMS value of triangular wave is this one. So if the capacitor is fairly large and the value of load resistance is very large, it can be assumed that the time T2 is equal to the half of the periodic time of the waveform. See in this figure, if capacitor value is more and RL value is more, then time period, this T2 is equal to T by 2, total time by 2. Total time by 2. So T is equal to 1 by F, 1 by 2F, then equation IDC by 2FC. So substitute equation this one, IDC by 2FC. Okay, this is the fifth equation. Substituting equation 5 in equation 4. So equation 5 in equation 4. So VRPP is equal to IDC by 2FC. In denominator, we will get extra term 2 root 3. 2 and 2, this 2 and this 2, 4 root 3. 4 IDC by 4 root 3 into FC. So what is IDC? IDC is equal to, current is equal to voltage by resistance, VDC by RL. So VDC by RL. So VRMS. So what is the ripple factor? Ripple factor formula is called VRMS by VDC. So VRMS is this one, VDC by 4 root 3 FC into RL into by VDC. So this VDC and this VDC cancel. Finally, we will get 1 by 4 root 3 FC into RL. Fc into RL. This is the ripple factor. So what do you mean by ripple factor? So in this capacitor problem, first we are given DC voltage, pulsating DC voltage is given like this. So pulsating DC voltage means it is having AC components and DC components. Then we are applying to filter. So filter output is like this. So here also some AC components are there. So by reducing these AC components, finally we will get the exact DC value like this. So how to minimize these AC components? So AC components in DC we call it as a ripple. So ripple factor of full wave rectifier is 0.48. Half wave rectifier 1.21. So these ripples are minimized by using proper capacitor, load resistance and frequency, these values. So for example, if load resistance RL in denominator is increases or capacitance is increases, what happen? These capacitor and load resistance are increases. So ripple value is decreases. Whenever denominator term is more means final value is reduces. So that based on capacitor and load resistance, selection of capacitor and load resistance, we will get the exact DC value. At the filter output. So this is called filter design. So filter design means we have to design such a way that the output of the filter which is having no ripples like this. So we will see one problem, you will clearly understood. So calculate the value of capacitance. To use in a capacitor filter connected to a full wave rectifier operating at a sinusoidal aircraft power frequency 400 Hz. If the ripple factor is 10% for a load of 500 ohm. So whenever data is given means write the given data. So ripple factor means it is there in percentage 10%. So we have to write 10 by 100, we will get 0.1 ripple factor. So frequency, so 400 Hz is the frequency. RL, load resistance is so this is the circuit, we know that. So this is the capacitor, this is the resistance, and this is the full wave rectifier. Output is given. So this is one block, this is one block. So this value we have to find capacitor value. We know the RL value. We know the ripple factor. So this is the formula. So ripple factor is equal to 1 by 4 root 3 Fc into RL. So we know that ripple factor 0.1 4 root 3 F 400 Hz, and C we want to find, and RL is the 500. So capacitor value is 72.2 microfarad. So this is the filter design, capacitor filter design. So by using 72.2 microfarad capacitor with the load resistance of 500, we will get only 0.1 ripple factor. 0.1 ripple factor means DC output is exactly same like this. DC output is like this. So it is exact DC look like. Okay. So this is the capacitor filter. So let us briefly recapitulate. So in this class, I talked about capacitor filter. So filters are 4 types. One is L filter, inductor filter, capacitor filter, or L filter or pipe filter. So in a C filter, capacitor is connected across the load. So we know that capacitor blocks DC and it allows AC. So that AC signals are reaches to ground, only DC signal appears at the output side. So finally we will get a rectified DC signal. So this is the filter, capacitor filter. Next class we will see some other type of filters like L filter,